So thank you very much for the invitation. For a large part of this talk will be, in some sense, fairly elementary, just reinterpreting things in terms of stacks. But I'm going to mention some applications of weighted blowups and these things. So, first of all, weighted blowups. So, for me, these will always be stack-theoretic. So, essentially, I always work with smooth stacks. So, classically, I mean, you do the approach of the Rydh algebra of an ideal. And what we're going to do here is that we're going to make weighted, meaning that we are going to replace our standard Rydh algebra here with some Rydh algebra which is not generated in degree 1. If you work classically with just ordinary approach, it doesn't make any difference because you can always take a sufficiently high power and make it generate in degree 1. But we're also going to make it stacky. So we're going to replace the usual approach with a stacky approach. And that it makes a difference. So for me, a Rydh algebra it's a finitely generated Oaks algebra called I dot, or I was thinking of ID TD. I also, for simplicity, I'm going to work with that-graded algebras, and the condition here is that, well, by definition it sits inside the one along the ring, but in negative degrees it should be everything. So equivalently, it's just a iteration of ideals etc. Such that here I have the structure sheet and it's finally generated.
Is X also a stack?
X could be a stack, but you can think of X as a scheme. So that's the Rydh algebra. And when you do the blowup of such Rydh algebra, we are taking the stack approach, so relative to X, which is just a spec relative to X, and subtract the irrelevant ideal and all that here, but take the stack quotient. And if you take positive or all, it doesn't matter. Classical. If it's just generated in degree in 1. All right, but we're going to work with smooth Rydh algebras, so it's smooth blowups, making the blowup smooth. So that the Rydh algebra is finally generated means that locally we can write it as the smallest algebra containing some generators. So by this I mean the smallest generated algebra containing x1 in degree d1 and also containing x1 in all smaller degrees by multiplying with T inverse. Let's say something like this, then I have x in degree 2 and y in degree 3, then I also have y in degree 2, and here I have have everything. But in degree 3, I don't have x, but I have x squared. And in degree 4, I also have x squared. And then I would have x cubed, y squared, y squared, etc. And reset by smooth. Locally, we can choose generators. As before, where a regular sequence and the vanish locus, which I'll call Z, of I1, which in this case is just the vanishing of a regular sequence if this is smooth. So what happens in contrast to usual blowups, it's not enough to just have the center to be smooth. I mean, you also need it really to be generated by a regular sequence locally. Otherwise, you could, for example, have something smooth with codimension R, but you actually need more than R generators, and then it's not going to be smooth. And if this is smooth, and X is smooth. It's a smooth stack. Okay, so how stack is this? I mean, if you're starting the smooth scheme, then I'm just modding up a GM. So it will have finite, even cyclic, finite abelian stabilizer. But typically we would make multiple blowups, so then it won't be cyclic anymore, but it will still remain abelian. In positive characteristic, I mean, like what has a new piece, so it need not be mounted in positive characteristic, but that's not. So some examples. If I take the blow-up on a linear subspace of n, I'm going to have charts which looks also like an, but I'll have new di stabilizer along the ith chart. So it's I mean, you have a very, very explicit presentation just as a blowups. But these also, I mean, they appear in nature. So I guess it's a theorem by Hausdorff, and also there's a 5-6 author paper this year, and I'm not, I'll try to think right now. So Arena, Di Lorenzo, Inchiostro, Rydh, Obina, Felicia. So they were interested in describing the Mantel computation of n-marked elliptic curves, and it emits a contraction to the Schubert modular stack of curves, so where you allow cusps, but you don't allow elliptic tails. And this is a way to flow up. So these are awful fun stacks. Wait for I guess we should have at least 2 points.
So it blows up something called codimension 2, right?
It blows up something called dimension 2, so it blows up exactly the locus. It blows up the locus it blows up the cusp of the locus, and it has coordinate 2, and here it has coordinate 1. So the exceptional divisor here is going to be where we have a genus 1 curve with no marked points, and then we have a genus 0 curve with n marked points. And it's going to blow down this elliptic tail and make a cusp here. So. But here the sensor here has. All right. So yeah. So we have the thing which happens here is that you have, when you do the stack of blowups, the exceptional divisor, it lives over your center, but it's not Cartesian. So it's not just how it is. And to illustrate this, if we do a blow up, so these are called root stacks. So if I take just one Cartesian divisor and place it in some degree d, then I have the blow up, the weighted stack-theoretic blow up here. Here I have d, and my e here is now going to be 0.1 over d. So pi is d is d times. So you can see that it's not equal.
So the blow up itself in this case isn't just a root stack?
It's as a root stack. So in the underlying core space is going to be X itself, so in this case this is going to be a core smaller space. And we are just introducing some stackiness along. Some UD here over the exceptional divisor. It's what projective? So pi is projective in a stacky way. So it's, I mean, you have the O1 on the blow up. I mean, it's O1 on the stack is going to kind of representations of the stacking of the stabilizers in this line bundle is going to be faithful, and the power of O1 is going to descend to the core space, and there it's an ample, relatively ample line bundle.
But it's probably not representable.
Pi is not representable, and that's the thing, that it introduces stackiness. So it's not projected in the scheme sense, but it's as close as being projected can be when you're not representable. And a final example, which is kind of the main example in some sense, is for so if you had a a fan, or more generally a stacky fan. So by which I mean a fan, and so it's going to be a simplicial fan. And a set of lattice points on the rays. Then from this data, we get a toric stack, which is a smooth stack with finite abelian stabilizers, and its core space is the usual toric variety, which of course is usually singular. And doing weighted, or like torus invariant weighted stack of blowups is nothing but making subdivisions of your toric fan. So if take a lattice point and write it as a sum of my generators, then if I want to understand I subdivide my fan divided at B, then the toric stack or this subdivided fan is going to be a weighted blowup of my toric stack, where I just pick the kind of intersection of the relevant torus divisors, but I need to take like a weighted intersection in terms of this ideal is going to be putting this toric divisors in the respective width. So the picture is something like, let's say I have a singular toric variety. Here's my row 1 and row 2. So an affine toric variety, and I want to resolve this, say. So I want to get this lattice point. I introduce this ray, and the way I can obtain this ray is by writing this V as 2 row 1 plus row 2. So when I've done the blow up, I will have I get other. So let's draw a picture perhaps. So we have D1 and D2, and it's singular at this point when the lattice generator has index 3, so this is going to be a mu 3 at this point, and then I do the blow up at this ideal generator, corresponding to this V. And then I have now D1 exception divisor E and D2, and now this cone is smooth, and this one now will be a mu2, but then we also have since I've now picked this generator, it's going to introduce a mu3 along this divisor. So here I have mu3, and the intersection point with D2 is actually even going to be a mu6. So if I take these two generators, they span something of index 6 in the full lattice.
So you can allow the row I to be primitive.
So yeah, I'm allowing this to not necessarily primitive, right?
So basically you take a Cox construction, right? stack with some
Yeah.
change of gradient.
So that's so Borisov, Chan Smith, I don't know, 20 years ago or something. And you can see all smooth weighted blowups are pullbacks from a toric situation. Locally, I can just pick my generators, x1 to xr, map to an, and then do a weighted blowup on the toric an, introducing some stackness and pull that back. But the kind of the strength is that we are not working in a situation, in a toric situation where everything is rational. You're really allowing yourself to work locally. So you could have stacks of general type and so on. But locally, everything reduces to toric geometry. And I'm also not working with like log structure, but really allowing myself to blow up any possible smooth locus with some weighted structure.
And you stack the generic to a scheme, or you don't care?
If I'm starting with a scheme or a stack with generic scheme, I remain so, right? So that's also my most interesting case would be that of Hausdorff's generic schemes. But I guess, like in this example of M1N, it's not generically a scheme, not generically a scheme. You have the hypothetic or the elliptic dimension. All right. So some application of weighted blowups. So there was this very nice recent result by Romish, Anthony Mudacic. So I don't know, is it 18 perhaps? Yeah, I should also mention McQuillan. So they do weighted embedded resolution singularities. So starting with you have some singular thing and embed it, which we can always do locally. Everything is going to be factorial locally, so this is now, if you solve this, then you have also solved resolving x. So then what they do is that they show that there exists a very nice invariant. So there's a very natural invariant. We call the order, actually some y. It doesn't quite take integers. But it's still going to be a bounded, well-ordered set. It is going to be some bounds that makes that if this decreases, it will go to 0 at some point. And there's also a very natural, smooth, weighted structure on the locus Z, which is the locus of where the invariant is maximal. And finally, if we take the weighted blow of this, then the invariant drops. So if I So this is a smooth thing, so this is still a smooth stack. But so now after this blow-up, maximum order. It's now strictly smaller than the maximum order of x anyway.
Is it in characteristic 0?
This is characteristic 0. No, so I mean so you mean this is weaker than Hironaka's result because you're doing weighted blowups instead of ordinary blowups and introduce stackiness. But the thing is that this is the most simplest possible invariant you can imagine that still is strong enough to do resolution. So it's really just the order of the order and also the center are locally given by hypostatic maximum contact. So it's literally going to look like that you have the first hypostatic maximum contact and you put it in, well, so the degree, you have to multiply degrees, but well, this is a different one degrees. And the invariant here is going to be d1. So the invariant kind of measures where you should put this hypostatic maximum contact, and also the Rydh algebra here actually also remembers the invariant. And now the one blow up, this drops strictly. And in positive characteristic, well, this doesn't work. I mean, you don't have hypostatic maximum contact. But still, this sheds some light over the algorithm that it avoids all the combinatorics you have to do with exception with trying to get the hypostatic maximum contact in good position with your centers, etc. So the usual algorithm would not decrease this. You would have to do lots and lots of blowups to decrease this. All right, so soon get to wall crossing, but first let me also mention destackification. So this is a result due to Daniel Berg, former student of mine. So this explains how if you have a smooth stack, how you can get rid of the stackiness. So here X is a smooth tame stack, not necessarily a waterfold, but for simplicity, let's say it has a coarse moduli space X. Then there exists, so here we have a very singular coarse moduli space, here we have a nice smooth stack. And it's going to desingularize X, but at the same time connect this desingularization with a smooth stack. So imagine, for example, starting here with just any variety with finite Cauchy singularities. There's a canonical resolution by a smooth stack. Now I'm going to connect this with a desingularization of X. So the claim is then that there exists a diagram where this is the core space. And this will be projective and birational. And this will be smooth. So the operations here is that I'm going to do blowups. But it's not quite enough blow-up, so P is a sequence of smooth blow-ups and smooth through stacks. stack. The simplest weighted blowups, either just on regular blowups or where you take a device and put it into BD. So they are smooth weighted blowups, but they are of this very, very special form. And pi is a sequence of smooth stacks. And you have so what perhaps a bit counterintuitive the first time you see this is that you actually have to add stackiness in order to remove the stackiness. There's no way of in a controlled manner remove the stackiness without first adding some extra. So you can see there is already for, I think when you have a U5, so you can have a cyclic singularity where you have to, where if you just do smooth ordinary blowups, you don't improve the singularity. I think it's a 1.5, 1.2, or.
This diagram, can it be made canonical?
It's canonical. It's highly canonical. And this is the it's very easy to solve this état locally on X. État locally, you just have a toric variety, and you just fill in. Well, in a Wheeling case. In a non-abelian case, you first reduce the Wheeling case. But in a Wheeling case, it's just a toric stack locally, and you can do pick your favorite lattice point that you want to draw a ray through, take some root stack so you can reach that point. I guess I erased this, but I took this 2 row 1 plus row 2. That's a way to blow up, but I could instead first take the root stack of row 1, then I get 2 row 1, and then I can take 2 row 1 plus row 2. So every way to blow up can be reached by first doing root stacks and then doing rows.
So the construction of XD is factorial.
Yeah, so this is that is a factorial with respect to smooth maps.
I'm still understanding of Julie Mumford.
We can also do this in Hausdorff characteristic. So this is a characteristic.
Sorry, but like for an art stack or just for
this and I'm assuming here course moduli space. And tame to me means
And in this previous theorem, where do you actually terminate? Is it like with the principalization or something?
The termination here? Yeah. So termination comes from just from the order decreasing. And
no, but what's the end result?
The end result is that X will become smooth. Will be a smooth Killing-Mumford stack. So what will happen is that at some point the order will be 1, 1, 1, 1, 1, 0, and that means that this is now a smooth sub-variety of Y, a smooth substack of Y.
Because if you blow it up, you'll get.
Then you'll get the visor, but you stop at the plasma. So here tame means that you allow mu p is okay, but alpha p not okay. And Z mod p is also not okay. So they should be linear deductive. We are allowing all étal prime to p groups and finite diagonalizable groups and étal groups which are finite. Okay, so one way now to do resolution singularities, first you do weighted resolution singularities, and then you do destackification of this. This is very effective, requiring far fewer blowups than your Nocus algorithm. This is extremely ineffective, so then it seems that you're great. But then my current student there is this highly effective destackification algorithm using weighted blowups, and again there's a fairly simple invariant that comes at each blowup.
What is the difference between effective and highly effective?
Yeah, that's well, effective. I mean, I guess it could mean that you're doing something that you can write down in constructive. It's a very efficient express. But it's in several order of magnitudes better than this algorithm. But the kind of so whenever there is, I mean, here these weights comes at you from the invariant of your Naka, then you should do weighted things. Here it's actually not quite as clear how you pick the weights, but there is, and I would say this is kind of canonical. This you can make some different choices. If you do bad choices, it's not so efficient.
So is that weighted blowups of the moduli space?
No. You're doing all my weighted blowups is on the stack level, so they're always smooth weighted blowups. Well, then you could interpret them as being some weighted blowups on the core space. But these are going to go for a smooth team stack, keep it smooth, and then make it into a smooth variety. Yeah, since this is the Rydh workshop, I should perhaps also mention something to Rydh. So, this is 17 perhaps, 16. So if you're starting with now a smooth proper game stack, well, if I'm in positive characteristic, let's write projective, because we can't do kind of a smooth Schauler then the perfect complexes on X is admissible subcategory of dB of smooth projective. So the proof is fairly direct from destackification in that original sense. So you have the Orlov blowout formula, and you also have a similar formula for the root stacks. So you know that you have X tilde is a nice drive category, and then the curly X tilde will be a summon, or it will have an admissible. It will have semi-total decomposition into nice categories, and then it follows that. So has X right by the Orlov blowout formula.
And do we have a blowout formula for the sticky weighted blowout?
Yeah, so that's perhaps it's known. I don't know. I also plan to have used the blow to investigate that, but it's something which is kind of hidden so far is that the accepted advisor is not just a projected bundle, a weighted bundle. So you can also, due to you have weights, it can also be twisted, so that I mean, it's only Zariski locally if you have a scheme. They're going to be a P of a Vex bundle with weights. So in general, it's like when you have Lewinsky rule that you will have AM vibrations. So the projected bundle is a bit more complicated in the weighted.
So what does it mean for the components of this semi-bundle composition?
For the root stack or for the
No, for the weighted blow-up, for the sticky weighted.
Yeah, so I don't know. Yeah. I'm presuming that there is something nice, but we know that they can be dominated by the two nice operations.
So is this X tilde or is something else?
Well, I mean, if I just do a single way to blow up, yeah, I don't know the formula. Well, that's the so wall crossing is of a different flavor because there you really have the weights attacking you, right?
But in the Kavanatas theory papers, doesn't we have something like that?
It's possible, yeah. Let me know about it and then I'll check it out. Yeah, I haven't showed such. I have no idea. So I'm going to do a stacky version of this. So it applies also when you don't have a GAT situation, but let's say, for example, the moduli space of curves, of the single curves, we don't know how to get GAT presentation of those. So GAT in this sense will just be a good moduli space. I'll do an example with a classical GAT. And variation of GAT will just consist of picking a line model. And when I pick this line model, this gives me two open subsets. Semi-stable. So this is the semi-stable locus with respect to L duo and with L. I have this good moduli space, and then I have this other good moduli spaces, which typically will be coarse moduli spaces. If some stability is equal to stability, and then I'll do this in bold space, and I have a projected match from these. So we're in. I mean, this is like a flip or a contraction. Let's do. So in GIT, I'm always going to work with linear reductives of, say, character 0, acting on the projective scheme in an ample line bundle. And now my kernel X is going to be the semi-stable locus with respect to this line bundle, modified by G, and X is the GAT quotient.
Probably X in a different form.
Right. That's why. This is trouble with working with stacks. That quite often the coarse moduli space, the good moduli space, has the same letter but different font, and then you write also the stack of quotient, and then you write. So variation GAT, and then you would pick another line model, a different linearization, which is the same thing as taking the difference of these two. So I'm picking a new line bundle here, and then we know that if I just take the semi-stable locus with respect to L and a very small multiple of M, it's going to be independent of epsilon. And these two things will now just be so this these things, and these will now be this modified unit. So working with stacks, I'm just picking the moduli space at the wall and taking the stack quotient, and I'm seeing my two nearby chambers of the subspace. At least to me, even when we are in a GAT situation, taking this stacky point of view is very, very helpful. Kind of clarifying situation. So perhaps I can also draw a picture. And now we have the linearization L here, and I'm picking two nearby linearization, and I'm going to compare the stack that I have here with the stack that I have on these two sides. So then we have the following, so which is kind of so if you read Dolgachev's or Thaddeus, when they're giving this in a slightly more restrictive setting, but I'm saying that this works in the following generality. I'll assume that X is smooth, and I'm going to assume that the stabilized dimension, well, I guess the stabilized dimension is at most 1. So that means that the stabilizers, well, if I take the connected reduced component, it's going to be. But it's okay with mu piece. It's also okay with non-abelian groups. I'm not assuming, and especially I'm not assuming that the stabilizer has G. So I think in Dolgachev they call this truly faithful, but they also assume that this whole thing is diagonalizable. But typical ball crossing in codimension model. And then, I mean, you could guess what I'm going to write. I mean, I haven't seen it written down in this way, but you know, it's not so difficult to guess. So there exists canonical, smooth, weighted structures. And we call it I dot plus on Z plus, which is X minus X plus. I think like Thaddeus, I think he calls this X upper index plus, which sorry, but this is the close. This is the attractor of the fixed locus, so to speak. So we have, and also on the intersection. But here I just take the sum of the plus and the minus. Let me call that, I'll press Z naught. And such that when I blow up,
The intersection is probably transverse.
that is transverse. Yeah, so these are all and this is transverse. So in particular, also this way to blow up in this will be the product of the way to blow up of these two. So if I blow up my X plus, then it's going to be very small because not X minus. Come on in. And these are really all canonical. So every wall crossing coming from a good moduli space, where you have GM stabilizers in the wall, comes from a weighted smooth blow-up, or a weighted smooth blow-down. Another nice thing is if you do the blow-up of the middle thing of X, well, it does not have a good moduli space anymore, but if you pick the semi-stable locus, so this is like a weighted Curwen blow-up, and this is going to be call this X tilde. This is going to be X tilde, but with a second root stack along the central divisor of these blobs. So the weighted Curwen is equal to these two common blobs.
What does S mean?
Yeah, let me explain. So it's a semi-stable locus, it's a relative semi-stable locus on this stack. So it's similar to, so here, I can really think of this X plus on a stack with this line model as a relative semi-stable locus. So if I take the powers of L, push it forward to the good moduli space, take global section, or pull it back.
But you change polarization.
I'm changing polarization. So you have to pick the right. It's actually, it's a bit, this polarization does not exist globally necessarily. So that's something you can't, if I'm starting a GAT situation, I can't give you the polarization here in terms of GAT. Because in different position of the model space, I need to take different routes about this time. I really have to pick a very precise linearization. So it's actually not the semi-stable locus with respect to line model. But locally.
It is a certain open substack of.
It's a certain open substack of the loop. Yeah, I'm not going to be able to say anything about open graphs.
So you could just see that the right-hand side embeds as an open substack and to make more
Let me perhaps do the picture here of 3 here. So if I do the usual Curwen, so I'm starting here with my wall here, and then I'll just do the unweighted blow up at the wall. Then I'm going to split this wall up in many walls. It's a line bundle that controls this, and I'm going to have here the Curwen blow up, and here I have X minus 1. Whereas if I do the weighted Curwen, so what I have here is that I'm going from my single wall to 2 walls. So here I have the X tilde square root of E, and then X plus and X minus. And now these are just blowdowns. So I can describe the middle, the Curwen as being just with 2 walls. But as I said, when picking out this open is, I can't do it globally. I can just describe it. Well, it's just going to be the, the complement of the 3 transforms of X plus and X minus. So that's. Sorry, of Z plus. But locally, it's going to be a semi-stable locus, and therefore it has good moduli space, etc. We can also retract the tractor and the repeller onto this. And these are going to be affine bundles. So I mean, there will be locally just non-standard graded polymer rings. And we can also describe on the level of the centers. So there exists some Km stack here, such that this becomes Cartesian. And now these are sorry, now we have to dissect this with x minus. These are now going to be projected by the bundles. It's just these minus the zero section. What's a bit delicate here is that you might have also like an asymptotic algebra that twists these. If your line bundle that you're starting with is not faithful on the GM.
You mean C path intersect x minus?
Well, so I've made this convention. Okay, now z plus intersect x plus is not empty. Okay. Yeah, sorry.
This issue with asymptotic algebra is the same as with the blow-up formula?
Yeah, I mean, right, exactly. No. So for the blow-up formula of way to blow up, you don't have an asymptotic algebra entering. It's only going to be like, I mean, you have an affine bundle. So you don't have a twisted GM there. I mean, as I wrote down the proj, it's just a proj mod GM. So there you have a GM quotient. This thing is not necessarily a GM quotient over this. Only locally. So I have exactly 2 minutes left, I guess. Let me just erase one part here. Yeah, perhaps I should also say, I mean, just as it would be nice with a formula like Hausdorff's formula for the way to blow up, it would also be interesting to compare these hypothetical formulas also with the work of Hausdorff and so on the orthogonal acquisition of the Rydh category in this situation. So just 1 minute on weak factorization. Let me say that all algorithms, I mean, they start with doing cobordism, so you're reducing to wall crossing. But the classical, I mean, if we do the algorithm of Ramesh, Karu, Matsuki, and Dacek, what they are doing there is that they are going from a wall crossing in this sense, and then they are reducing it to smooth toric varieties, and then they're doing toric factorization. So you can imagine, I mean, this involves resolution in singularities, etc. So as an algorithm, all of this is kind of costly. But when you got to the wall crossing, you are, I mean, because in this wall crossing, I mean, these will typically be, I mean, they have typically finite portion singularities, and they're also not toric, but they're locally toric. So this is the process of torification, and also doing more resolution singularities. Then you're in a situation where it's really not even toric but toroidal, and then you use Dacek's with factorization of toric varieties. But just doing the, I mean, we have now the wall crossings are just given by smooth. So we weighted. We can directly go to weighted factorization from the wall crossing situation. I just have a half minute more. I also forgot to say that a corollary of this is that for any MGN, this is a weighted blow-up. And this is because it has been constructed a good moduli space which exhibits this as a wall crossing. So it's a immediate consequence from the wall crossing theorem. You get a smooth weighted blow-up without having to construct.
Do you still need any bigger than equal to 1?
Sorry? Yeah. Well, I guess G and N should be. So it's not empty. Okay, thank you.